All right. Hello, my name is Johan. Our group is comprised of me, Alan, Alte, and Christian. We are the trigger generator team. The focus for our senior design project is to develop a compact mobile trigger generator capable of driving a high voltage spark gap switch. In particular, we are designing a trigger generator to work with a 3-electrode spark gap switch, which provides versatility and control in pulse power applications. Our design seeks to produce a pulse with 400 nanoseconds of rise time, 2 microsecond duration, a 50 hertz repetition rate, and minimal jitter. The project's design emphasizes compactness, portability, and precise control.
Moving on to the background, our compact mobile trigger generator relies on pulse power technology, which generates short, high-intensity bursts of electrical energy for applications such as pulse power systems and spark gap switches. So how does the spark gap operate? By using dielectric breakdown, where a high voltage ionizes the insulating gas to create a conductive plasma channel, such as an arc, allowing current to flow between 2 electrodes. What's important to take into consideration is Paxton's law, which will be shown in figure 1, which governs breakdown voltage based on gas pressure and the gap distance between electrodes. And this law basically creates a Paxton's curve to visually find the minimum voltage breakdown of the gas. The trigger generator utilizes a high voltage pulse transformer and capacitor-based discharge circuit to deliver fast, controlled pulses necessary for voltage breakdown and reliable spark gap operation. To ensure safety, minimize interference, and maintain signal integrity, galvanic isolation is implemented using transformers, preventing unwanted electrical conduction between system components, specifically between our high voltage and our low voltage components. By precisely timing the energy transfer, the system ensures consistent triggering while maintaining efficiency and compactness. And as we can see in figure 1, we see the Paxton's law, which is comprised of gas constants, the distance between electrodes, the gas pressure, and secondary electron emission coefficients. Figure 2 shows Paxton's curves, and where at the bottom we'll be able to identify the breakdown voltage. And then figure 3 is a spark gap switch that's typical for commercial industries.
For the trigger generator to be portable, our project is designed with a battery power source in mind. That battery voltage is set down to 5 volts for the secondary circuitry using a 7805 voltage regulator. And also that goes to the fiber optic receiver and the gate driver for our IGBTs. At that same time, that battery voltage is also stepped up to 200 volts for our charge circuit and our pulse transformer. The pulse transformer is able to output a peak voltage of 20 kilovolts, which is what the 200 volt step up is to accomplish. The charge circuit is made up of a capacitor within a snubbing circuit to prevent ringing on discharge and a resistor to prevent overcharging that is sized for our 50 hertz repetition rate. This charge circuit can then dispatch a high voltage pulse to the spark gap and use the trigger electrode to create a spark. And now on to our experiment components.
For the spark gap design, we wanted to create a closed and secure model to run experimental tests where we incorporate the dielectric breakdown for air, nitrogen, and argon. Final assembly of it is shown in figure 5 using Autodesk Inventor. The way the design works is the electrode, which is labeled part 1, are connected to a precision flange nut, which is part 5, on the end of the base. One is designated to be set, the other can move through an O-ring built within a precision flange inside the acrylic housing, which is shown in figure 6 below. Both ends of the housing is covered with the milled acrylic base, part 4, where the precision flange and gas inlet, or part 2, are placed. These bases are then sealed with nylon-threaded rods and hex nuts to avoid leakage. Wires will be attached to the screws through the conductive precision flange, as well as a connection to our trigger electrode that will be connected to our main circuitry, which is presented in the PCB.
All right. Figure 7 shows some simulation results, our circuit diagram, as well as a PCB. According to the simulation, the circuit should provide a clean 20 kilovolts pulse with fast time, rise time, and duration. The duration of the pulse can be adjusted by raising the capacitor value, and the PCB is assembled but must be tested under direct supervision due to high voltages. Now on to our conclusions. During this project, we designed a mobile trigger generator using an interdisciplinary approach combining electrical engineering, material science, and digital control systems. We overcame challenges in crafting components such as circuitry and the spark gap, gained experience working with high voltages and industry standards, and developed knowledge applicable to the real-world power industry scenarios.